So, here's something worth thinking about as you settle in tonight. Right now, as you lie there, your body is tracing a path through space. The Earth is turning, carrying you eastward at nearly 1,000 miles per hour. At the same time, you are orbiting the Sun at about 67,000 miles per hour, and your entire solar system is moving through the Milky Way galaxy at roughly 450,000 miles per hour. But here is what makes that interesting. In this quiet moment, you are not aware of any of that speed, any of that motion. You feel still, you feel at rest. And that simple feeling, that simple fact, that motion can be happening all around you, all through you, and yet you can be completely still, is a kind of puzzle. It is a puzzle that took thousands of years for humans to even begin to understand. It is a puzzle that touches on the very nature of time, of space, of how things move and why they move the way they do. It is a puzzle that asks, in its simplest form, how can something be changing and yet seem so still? How can you be moving so fast and yet feel nothing at all? How can the world be in such constant motion and yet your experience of it be so calm? And tonight, we are going to explore that puzzle and the system of thought that was built to solve it. Tonight, we are going to go through all of calculus, from the very beginning, its history, its core ideas, all the way through to how it works in the world around you at this very moment. You will not become a mathematician by the end of the night, but you will understand what calculus actually is, not just a class you took or heard about, but a way of seeing change, motion, growth, and decay. You will understand why it was invented, what problem it solved, and how its quiet logic governs everything from the phone that might be on your bedside table, to the beating of your own heart, to the orbit of the moon above you. We will take this slowly, step by step, because calculus is not something that needs to be rushed. It is something that unfolds, like a story, like a gradual awakening to the way the world works, and by the time the night is over, you will have a sense of the whole shape of it, the grand arc of the idea, from ancient geometry to modern physics, from the measurement of a plot of land to the prediction of a comet's return. Calculus is not just a branch of mathematics. It is a way of thinking that has shaped the entire modern world. It is the intellectual foundation upon which our technological civilization is built. Every bridge you have ever crossed, every skyscraper you have ever seen, every airplane you have ever flown in, they all exist because someone used calculus. Every time you send a text message, every time you watch a video online, every time you use a map on your phone, you are relying on the mathematics that Newton and Leibniz developed centuries ago. And tonight, you are going to understand it, not as a set of formulas, but as a living, breathing idea. And if you fall asleep somewhere along the way, that is perfectly fine. That is the point. These ideas are not going anywhere. They have been here for centuries, and they will be here when you wake up. You do not need to remember every name or every detail. You only need to let the shape of the story settle into your mind. There is no test at the end of this night, only a deeper quiet and a gentle understanding. So let your body sink into the mattress. Let the weight of the day begin to lift, and we will start at the very beginning, long before calculus had a name, long before anyone knew what it was. We will start in a time when the world was still a place of mystery, and the movements of the heavens were the province of gods and spirits. We will start in a time when humans looked up at the stars and saw not laws, but stories. And we will watch, slowly, as human beings began to see patterns, began to measure, began to understand. To understand calculus, you have to go back to a time when people were just beginning to look at the world with measuring tools. The ancient Greeks, around 500 years before the birth of Christ, were among the first to try to think about shapes and space in a logical way. They were not trying to invent calculus, not yet. They were trying to understand the world through geometry. Geometry was their language for describing the earth, the sky, the lines of a building, the path of a ship, and they were very good at it. They could calculate the area of a circle, the volume of a sphere, the angles of a triangle. They could measure the distance to the horizon. They could calculate the height of a pyramid by measuring its shadow. They could determine the circumference of the earth with remarkable accuracy, using nothing but a stick and the angle of the sun. They could calculate the distance from the earth to the moon using parallax, a method that involves observing the moon from two different points on the earth. Their geometry was elegant, beautiful, and powerful. It was a system of thought that was logical, consistent, and applicable to many problems. The mathematician Euclid, who lived around 300 years before Christ, wrote a book called The Elements that organized all of the known geometry of his time into a single logical system. This book was so influential that it was used as a textbook for over 2,000 years. It contained definitions, axioms, and proofs that built up the entire edifice of geometry from a small set of basic assumptions. It was a masterpiece of logical thinking, and it set the standard for all of mathematics that followed. But even with all of this power, Euclid and his fellow Greeks ran into a problem, one that would frustrate them for centuries. The problem was this: they could measure things that were straight, things that were flat, things that were simple. But the world is not straight or flat or simple. The world curves. It moves. It changes. And their geometry, as elegant as it was essentially a geometry of stillness. It could describe a moment, but not the passage of time. It could measure a line, but not the speed of an object moving along it. It could calculate the area of a square, but it struggled with the area of a shape with curved edges. It could tell you where a planet was at a given time, but it could not predict where it would be tomorrow. That was the puzzle that sat at the edge of their understanding. They could see the world in motion, they could feel time passing, but they could not capture it in their mathematical language. It was like having a dictionary that contained only nouns, no verbs. They could name things, but they could not describe what they did. They could describe the shape of a river, but not the flow of the water. Take, for example, the simple act of walking across a room. The Greeks could measure the room. They could tell you its length, its width, the area of the floor. They could tell you the volume of the air in the room, if they knew its height. But if you walked across that room, they could not tell you, precisely, your speed at any given instant. They could measure the total distance and the total time, and they could calculate an average speed. They could say that you walked at a rate of 4 feet per second on average, but they could not capture the moment of acceleration, the slight change in your pace as you began to walk, or the slowing down as you approached the other side. Those were mysteries. Those were hidden. The tools of geometry were static, frozen in time, while the world was dynamic and flowing. This was the great divide, the gap between the static and the dynamic, the gap between what could be measured and what could only be observed. And it was not just a problem for the Greeks. It was a problem for everyone who had ever watched a bird fly, a leaf fall, or a river flow. It was a problem for farmers who wanted to predict the growth of their crops, for sailors who wanted to navigate the open sea, for builders who wanted to construct arches and domes. It was a problem for astronomers who wanted to understand the motion of the planets, for engineers who wanted to build better machines, for philosophers who wanted to understand the nature of time itself. The world was in motion, but the language of measurement was at rest. And that was the problem that calculus would eventually solve. And it was not just motion, it was also shape. The Greeks could find the area of a rectangle, a triangle, a circle. They had formulas for these shapes, elegant formulas that they had derived from first principles. The area of a rectangle is its length times its width. The area of a triangle is half its base times its height. The area of a circle is pi times the square of its radius. These are beautiful and simple formulas, but the area under a curve, a parabola, a shape that arches and flows, that was much more difficult. A parabola is the shape of a thrown ball, or the shape of a suspension bridge cable. It is a curve that is not straight, not circular, but something else. It is a shape that changes direction smoothly, that rises and falls in a graceful arc. The Greeks could approximate the area under a parabola by drawing rectangles under it and adding up their areas. But the approximation was never exact. It was always a little too small or a little too large, and they knew it. They knew that their calculations were only approximations, not true, exact answers. And this is where a man named Archimedes comes in. Archimedes lived in the 3rd century BC in Syracuse, on the island of Sicily. He is one of the most brilliant minds of the ancient world, a mathematician, a physicist, an engineer, and an inventor. He is famous for many things, including the principle of buoyancy, which is the reason that ships float, and for the story of running through the streets shouting Eureka after he discovered that principle. And he wrestled with this problem of the curved and the changing. He developed a method, a kind of pre-calculus, that he called the method of exhaustion. The idea was simple and beautiful. If you want to find the area under a curve, you draw shapes inside it, shapes whose area you know, like rectangles or triangles. And then you draw more shapes and more shapes, filling the space more and more tightly. As you increase the number of shapes, your approximation gets closer and closer to the true area. Archimedes understood that the true area was the limit of this process, the value that you approached but never quite reached. He did not use the word limit, but he understood the concept. He understood that if you could keep adding shapes forever, you would get arbitrarily close to the true area. He used this method to calculate the area of a parabolic segment, and he was very proud of this result. He also used a similar method to calculate the volume of a sphere, and he discovered that the volume of a sphere is exactly 2/3 the volume of the cylinder that surrounds it. He also calculated the volume of a cone, and he discovered relationships between these volumes that had never been seen before. This was a profound insight. He was thinking about infinity, about the infinite, and about the limit, which are the very foundations of calculus. But he did not have the language or the formal system to express it fully. He could do it for specific shapes like the parabola, but he could not generalize it. He had found a glimpse of the idea, but he could not turn it into a tool that anyone could use. His work was a brilliant island in a sea of static geometry. And then, the path to calculus went dark for a long time. The fall of the Roman Empire, the rise of the Middle Ages, the loss of ancient texts, the focus on other kinds of knowledge, all of these things delayed the next great step. The puzzle of the changing and the curved sat, waiting, for more than 1,000 years. It sat in the libraries of Constantinople, in the monasteries of Ireland, in the courts of the Islamic caliphates. It waited for someone to pick it up again. But ideas do not die, they sleep. And in the 15th century, with the Renaissance, a rebirth of learning and inquiry, those ideas began to wake up. Scholars in Europe rediscovered the works of Archimedes and other Greek mathematicians. They began to translate them, to study them, to build upon them, and slowly, over the course of 200 years, the pieces began to come together. There were many contributors. There was Johannes Kepler, the astronomer who discovered the laws of planetary motion. He was trying to understand the orbits of the planets, and in doing so, he thought about the area swept out by a planet as it moves around the sun. He realized that the area swept out in a given time is constant. This is Kepler's second law of planetary motion. But to prove it, he needed a way to calculate areas of curved shapes. He used methods that were similar to Archimedes, but he pushed them further. There was Galileo Galilei, the father of modern physics, who studied motion. He dropped objects from the Leaning Tower of Pisa, or so the story goes, and he studied the way they fell. He realized that the distance an object falls is proportional to the square of the time it has been falling. That is, if you drop a ball, it will fall 4 times as far in 2 seconds as it does in 1 second. This is a fundamental insight about the nature of acceleration. But Galileo, like Archimedes, did not have the full language of calculus. He was building the foundation, brick by brick. There was René Descartes, who developed the coordinate system that we still use today. He showed that you could represent geometric shapes using equations, and that you could represent equations using geometric shapes. This was a crucial step because it allowed mathematicians to think about curves in a new way. It allowed them to see the connection between algebra and geometry. Instead of drawing a curve, you could write an equation for it. Instead of looking at a shape, you could analyze its equation. There was Pierre de Fermat, who developed a method for finding the maxima and minima of curves. He was getting very close to the idea of the derivative. He could find the highest point of a curve, or the lowest point, but he could not yet describe the slope at every point. And there was Isaac Barrow, who was Newton's teacher, and who understood the relationship between the tangent to a curve and the area under a curve. He was on the verge of the fundamental theorem of calculus. He knew that these two things were connected, but he could not quite see how. So by the middle of the 17th century, all of the pieces were in place. The foundation was complete. The structure was ready to be built. It was not until the 17th century, more than 1,000 years after Archimedes, that the pieces finally came together. And they came together in the minds of two men, working independently, often in competition, across the channel between England and continental Europe. Their names are Isaac Newton and Gottfried Wilhelm Leibniz, and they are the two main figures in the story of calculus. They did not invent it in a vacuum. They stood on the shoulders of Archimedes and of Kepler and of Galileo and of Descartes and of Fermat and of Barrow and of many others who had kept the ancient mathematical traditions alive through the medieval period. But they were the ones who created the system, the language, the rules that turned calculus into a practical and powerful tool. And they are the ones who argued bitterly over who discovered it first. Newton claimed that he had invented calculus in the 1660s, but he did not publish his work until much later. Leibniz published his work in the 1680s, and his notation was so clear and elegant that it became the standard. The argument over priority was bitter and lasted for decades. It divided the mathematical community of Europe into two camps, the English followers of Newton and the continental followers of Leibniz. It was a dispute that involved politics, national pride, and personal animosity. The Royal Society in England, which was the leading scientific institution of the time, became involved in the dispute. It was a messy and unseemly affair, and it did not reflect well on anyone involved. But tonight, we are less interested in the argument than in the ideas themselves. The ideas are what matter. The ideas are what have shaped the modern world, and the ideas are what we are going to explore, slowly and gently, for the rest of the night. The idea that Newton and Leibniz discovered, each in their own way, is that there are two fundamental operations at the heart of calculus. These two operations are like two sides of the same coin. One is about taking things apart, and the other is about putting them together. One is about measuring change at an instant. The other is about measuring the accumulation of change over time. They are inverse processes, each one undoing the other. And this relationship is the deepest, most beautiful thing about calculus. It is what makes calculus more than just a collection of tricks. It is what makes it a unified system of thought. Newton called his method the method of fluxions, a word that is no longer used. Fluxion comes from the Latin word for flow, and that is exactly what Newton was thinking about. He saw the world in a state of constant flow. He saw quantities flowing, changing, moving. He called the flowing quantities fluents, and the rates of change, the speeds, he called fluxions. For him, calculus was the mathematics of flow. He imagined a point moving along a curve, and the fluxions were the velocities of that point in the x and y directions. He thought about time as the universal variable, the river in which everything else flows. Leibniz, on the other hand, developed a different notation, a different language. He was a philosopher as well as a mathematician, and he thought in terms of infinitesimals, tiny, almost zero quantities. He imagined a curve as being made up of an infinite number of infinitely small straight lines. He imagined motion as being made up of an infinite number of infinitely small jumps. His notation was so elegant, so clear, that it is the notation we use today. When you see the symbol that looks like a long S, that is Leibniz's notation for an integral, for the process of putting things together. And when you see the symbol that looks like a D, meaning a very small change, that is also Leibniz's notation. The D stands for difference, for a tiny, tiny difference, an infinitesimal change. So two men, two approaches, one grand idea. The idea that we can understand the universe by understanding its changes, and that we can build a language to describe those changes precisely, a language that is the language of calculus. So let us begin with the first of those two fundamental operations, the one that looks at change at a single moment. It is called the derivative. The derivative is the mathematical way of asking a very simple question. The question is this: at this exact instant, how fast is something changing? Imagine you are in a car and you look at the speedometer. The speedometer does not tell you the average speed over the entire trip. It does not tell you the distance you have traveled. The speedometer tells you your speed right now, at this very moment. That is the derivative. It is the speedometer of a mathematical function. It is the instantaneous rate of change. But how do you measure something at an exact instant? How do you measure the speed of a car at a single point in time? You cannot measure speed without time passing. You cannot measure motion without a before and an after. Speed requires 2 points in time to compare. But if you take 2 points in time, you are measuring an average. You are measuring the total distance divided by the total time. That is not the instantaneous speed. That is something else. To get the instantaneous speed, you would need to measure the distance traveled in a period of time so small that it is essentially zero. And that is where the derivative gets its power. You calculate the average speed over smaller and smaller intervals of time. You take a tiny interval, and then a tinier one, and then a tinier one. You measure the distance traveled in that tiny interval, and you divide by the length of the interval. And you watch the average speed approach a particular value. That value is the limit, and that limit is the instantaneous speed. The derivative is that limit. It is the speed that the average speed approaches as the time interval shrinks to nothing. It is the slope of the line that just touches the curve at a single point. A line that touches a curve at exactly one point, and no other, is called a tangent line. The derivative is the slope of that tangent line. It is a way of measuring the steepness of a curve at any given point. If the curve is flat, the derivative is zero. If the curve is going up, the derivative is positive. If the curve is going down, the derivative is negative. If the curve is getting steeper, the derivative is getting larger. If the curve is leveling off, the derivative is getting smaller. And this is where the power of the derivative really begins to show itself. The derivative is not just a number. The derivative is itself a function. It is a function that describes the slope, the steepness, at every point of the original function. It is a map of the original function's rate of change. So if you have a function that describes the position of a car over time, its derivative describes the velocity of the car over time. And if you take the derivative of the velocity, you get the acceleration of the car over time. You are getting at deeper and deeper levels of change. And this is the derivative, the first of the two great operations of calculus. It is the tool for understanding motion, for understanding the flow of a river, the growth of a plant, the decay of a radioactive atom. It is the tool for understanding how anything changes. Now let us look at the second operation, which is the inverse of the derivative. It is called the integral. Where the derivative takes things apart, the integral puts things together. Where the derivative asks, how fast is this changing right now? The integral asks, how much has accumulated over time, or space? It is the total, the sum of all the little pieces. And this is a very different way of thinking. The derivative looks at the present moment, a single instant. The integral looks at the whole journey, the entire span. The derivative is the microphone, picking up the sound at this very second. The integral is the total sound over the entire song. The derivative is the speedometer. The integral is the odometer. If you know how fast you are going at every moment, the integral can tell you the total distance you have traveled. That is the magic of the integral. It takes the rate of change, the derivative, and turns it back into the original quantity. It undoes the derivative. And this is the second part of the grand discovery of Newton and Leibniz, the thing that made calculus a complete system. They realized that the operation of finding the area under a curve and the operation of finding the derivative are inverses of each other. This is called the fundamental theorem of calculus, but in many ways it is the only theorem you really need to understand. The fundamental theorem says that differentiation and integration are inverse operations. One undoes the other. This is a deep and practical insight. It means that if you want to find the total change in a system, you can look at the rate of change and integrate it. If you want to find the rate of change at a given moment, you can look at the total and differentiate it. The two operations are mirrors of each other, and together, they provide a way to analyze anything that changes, flows, or accumulates. They provide a way to see the relationship between the small and the large, the local and the global, the instant and the whole. Let us think about this in terms of a simple example, a plant growing. Suppose you are watching a sunflower grow taller over a summer. You measure its height each day, and you plot those measurements on a graph. The graph is a curve that climbs upward, maybe faster on some days and slower on others. Now, if you wanted to know the average rate of growth over the whole summer, you would look at the total growth and divide by the number of days. That is simple arithmetic. But if you wanted to know how fast the sunflower was growing on a particular day, maybe the hottest day in July, you would need the derivative. You would look at the slope of the curve on that day, and you would say, on that day, the sunflower was growing at this rate, for example, 1 centimeter per day. That is the derivative. Now suppose you knew the rate of growth for each day. Say you had a little machine that measured the growth speed every hour. If you wanted to know the total height of the sunflower at the end of the summer, you could take all of those little rates, all of those tiny changes in height, and add them all up. That is the integral. You are putting together all the little pieces to find the total. The derivative tells you the speed at any moment. The integral tells you the total distance covered. And the fundamental theorem says that if you integrate the derivative of the height, you get back the height itself. They are inverse operations. They undo each other. It is a perfect circle of understanding. And so the story of calculus is the story of these two ideas, the derivative and the integral, and the fundamental relationship between them. But it is also the story of how these ideas were built upon, extended and deepened by many thinkers who came after Newton and Leibniz. The 18th century saw the work of the Swiss mathematician Leonhard Euler, who did more to advance the language of calculus than perhaps any other single person. Euler is one of the most prolific mathematicians in history. He wrote more than 70 volumes of mathematical work. He introduced many of the symbols we use today, including the notation for a function, the symbol for pi, and the symbol for the imaginary unit. And he developed methods for applying calculus to problems of physics, astronomy, and engineering. He made calculus a practical tool, not just a philosophical curiosity. He showed that calculus could be used to describe the flow of fluids, the vibration of strings, and the motion of the planets. He formulated the equations of motion for a rigid body, and he made fundamental contributions to the study of differential equations. He also developed the calculus of variations, which is a method for finding the path that minimizes or maximizes a quantity. This is a powerful tool for solving optimization problems. The 19th century saw the work of Augustin Louis Cauchy, a French mathematician who, along with others, put calculus on a rigorous logical foundation. This is often called real analysis. It is the formal system that defines exactly what a limit is, exactly what continuity means, exactly what an infinitesimal is. This was important because Newton and Leibniz had used intuitive ideas that were not always logically clear. They had talked about infinitely small quantities, but they had not always been able to define them precisely. Cauchy and others cleaned up the mess, made the logic airtight, and gave us the modern calculus that is taught in universities today. They introduced the epsilon-delta definition of a limit, which is a rigorous way of saying that a function approaches a particular value. They defined continuity in terms of limits, and they proved many of the theorems that Newton and Leibniz had taken for granted. They also developed the theory of series and sequences. So the history of calculus is not just the story of two men. It is a long story of humans trying to understand change, a story that stretches from the geometry of ancient Greece to the rigorous analysis of the 19th century and beyond. It is a story of collaboration, of competition, of brilliant flashes of insight, and of painstaking work to fill in the gaps. And it is a story that is still being written today. If you are still with me, let your eyes close now if they are not already closed. You do not need to follow every word from here. Just let it wash over you. The explanation continues either way. Let us now spend some time with the derivative. The derivative is the operation that captures instantaneous change. To get a derivative, you start with a function, which is just a rule that takes an input, like time, and gives an output, like distance. The derivative of that function is a new function, and it tells you how the output changes when you make a tiny change to the input. If you increase your input by a tiny amount, your output changes by some amount. The derivative is the ratio of the change in output to the change in input in the limit, as that change in input approaches zero. This is the definition of the derivative, and it is perhaps the most important definition in all of calculus. It is the mathematical expression of the concept of instantaneous rate of change, and there are several important rules that make finding derivatives a matter of procedure. The first is the power rule. This rule states that if your function is one variable raised to a power, like x squared or x cubed, then the derivative is that power multiplied by the variable raised to one less power. So the derivative of x squared is 2 times x. The derivative of x cubed is 3 times x squared. The derivative of x to the 4th power is 4 times x cubed. This rule captures the idea that the rate of change of an exponential relationship is itself an exponential relationship, but one step down. If you have a function that describes the volume of a sphere as a function of its radius, you can use the power rule to find the rate at which the volume changes as the radius increases. There are also rules for sums, for differences, for products, and for quotients. The product rule, for example, tells you how to find the derivative of a product of two functions. It says that the derivative of the product is the derivative of the first function times the second function, plus the first function times the derivative of the second function. This is a bit of a mouthful, but it is a very useful rule. It is used whenever you have two quantities that are both changing, and you want to know the rate of change of their product. For example, if you have a rectangle whose length and width are both changing with time, the product rule tells you how fast the area of the rectangle is changing. The quotient rule tells you how to find the derivative of a ratio of two functions. It says that the derivative of the quotient is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator. This is a bit more complicated, but it is also very useful. It is used whenever you have a ratio of two quantities that are both changing. There is also a rule called the chain rule, which is one of the most powerful and important rules in all of calculus. The chain rule tells you how to find the derivative of a function that is composed of another function. That is, a function inside a function. For example, Suppose you have the square of the sine of x. The sine of x is the inside function, and the square is the outside function. The chain rule tells you to take the derivative of the outside function, evaluate it at the inside function, and multiply it by the derivative of the inside function. So the derivative of the square of the sine of x is 2 times the sine of x times the cosine of x. This is a powerful and subtle idea because it allows you to break down complex changes into a series of simpler changes. It allows you to understand how a change in the input propagates through a series of operations to produce a change in the final output. This is a very natural way of thinking about the world. A small change in temperature leads to a small change in pressure, which leads to a small change in volume, and so on. The chain rule captures that chain of causation in a precise mathematical way. It is the rule that makes calculus applicable to so many different fields, because the world is full of nested dependencies. It is the rule that allows us to model complex systems with many interacting parts. Now let us turn to the integral, the operation that accumulates change. There are 2 main types of integral. The first is the indefinite integral, which is also called the antiderivative. This is simply the inverse operation of the derivative. If you have a function and you want to find another function whose derivative is the original function, you are finding the indefinite integral. It is like asking, what function, when differentiated, gives me this? The answer is never unique, because adding a constant to a function does not change its derivative. The derivative of a constant is 0, so the indefinite integral always includes an arbitrary constant, often denoted by c. This constant represents the fact that there are infinitely many functions that have the same derivative. They are all vertical shifts of each other. This is not a problem, it is just a fact of life in calculus. The second type of integral is the definite integral. This is the operation that finds the total accumulation of a quantity over a specific interval. If you want to know the total distance traveled between 2 points in time, you use a definite integral. If you want to know the total area under a curve between 2 points on the x-axis, you use a definite integral. The definite integral is a number, a single value that represents the total accumulation. And here is where the fundamental theorem of calculus comes into play. The fundamental theorem says that if you want to evaluate a definite integral, you can find the indefinite integral of the function, and then you evaluate that indefinite integral at the upper limit of the interval and subtract the value at the lower limit of the interval. This is a computational shortcut. It means that instead of having to add up an infinite number of infinitely small pieces, you can just find the antiderivative and do a simple subtraction. This is what makes calculus so powerful in practice. It is the reason that calculus is a tool for engineers and scientists, not just a philosophical exercise. It is the reason that you can calculate the area under any curve, as long as you can find the antiderivative of the function that defines the curve. It is the reason that you can calculate the total work done by a force, the total charge stored in a capacitor, the total volume of a solid of revolution. And there are many rules for integration as well. There is the power rule for integrals, which is the reverse of the power rule for derivatives. It says that the integral of x to the power n is x to the power n plus 1 divided by n plus 1 plus a constant. There are rules for integrating sums and differences. There is a technique called integration by substitution, which is the reverse of the chain rule. In this technique, you change the variable of integration to make the integral simpler. You substitute a new variable for a function of the old variable, and you adjust the differential accordingly. This is a very common and powerful technique. It is used whenever you see a complicated function that can be simplified by a change of variable. And there is a technique called integration by parts, which is the reverse of the product rule. This technique allows you to integrate a product of 2 functions by breaking it into simpler parts. It is based on the product rule for derivatives, and it is one of the most useful techniques in all of calculus. It is used whenever you have a product of two functions that are not easily integrated together. These are the tools of the trade, the practical methods for finding derivatives and integrals. But it is important to remember that these are just rules. They are built on the deeper ideas, the ideas of limits and infinitesimals, and the inverse relationship between differentiation and integration. The derivative and the integral are the two fundamental operations of calculus, and the fundamental theorem of calculus connects them. That is the whole story, in its simplest form. But of course, there is more. There are many extensions and variations of these ideas. One variation is multivariable calculus. In the basic calculus we have been talking about, you have one input and one output. But in the real world, most things depend on many variables. The temperature of the air in this room depends on where you are in the room, and on time. It depends on 3 spatial coordinates and 1 time coordinate. That is 4 inputs. The pressure of the air depends on temperature, volume, and the number of gas molecules. That is 3 inputs. Multivariable calculus extends the ideas of derivatives and integrals to functions of more than one variable. The derivative becomes a vector, a collection of partial derivatives, each one measuring the change in the output with respect to one particular input while holding the others constant. A partial derivative is a derivative with respect to one variable, treating all the other variables as constants. For example, if you have a function that describes the temperature of a room as a function of x, y, and z, the partial derivative with respect to x tells you how the temperature changes as you move in the x direction, keeping y and z fixed. The collection of all these partial derivatives is called the gradient, and it points in the direction of the steepest increase of the function. This is the mathematical language of the physical world. It is the language of fields, like gravitational fields and electromagnetic fields. It is the language of flows, like the flow of heat or the flow of a fluid. Multivariable calculus is what allows us to understand how water flows around a rock, how air moves over an airplane wing, and how heat spreads through a metal rod. It is essential for understanding the weather, the oceans, and the atmosphere. It is the calculus of the real world, the calculus of three-dimensional space and time, and it introduces new concepts like the divergence and the curl, which measure how a vector field spreads out or rotates. These are the tools of fluid dynamics and electromagnetism. Another variation is differential equations. A differential equation is an equation that involves a function and its derivatives. It is a relationship between a quantity and its rate of change. These are the most important equations in all of science and engineering. The laws of motion, the laws of electromagnetism, the laws of thermodynamics, all of them are differential equations. They describe how things change over time. To solve a differential equation is to find the function that satisfies the relationship. This is a large and deep branch of mathematics, but it all rests on the foundations of calculus. There are ordinary differential equations, which involve functions of a single variable, and there are partial differential equations, which involve functions of multiple variables. Ordinary differential equations are used to model the motion of a pendulum, the growth of a population, or the cooling of a cup of coffee. Partial differential equations are used to model the flow of heat, the vibration of a drumhead, or the propagation of light. The equations of fluid dynamics, known as the Navier-Stokes equations, are partial differential equations that are among the most challenging and important in all of mathematics. They describe the motion of fluids, from the flow of air over an airplane wing to the flow of blood through the human body. And there is vector calculus, which is the application of calculus to vector fields, quantities that have both a magnitude and a direction. This is the language of fluid dynamics and electromagnetism. It includes important theorems like the divergence theorem and Stokes' theorem, which are elegant and powerful extensions of the fundamental theorem of calculus to higher dimensions. The divergence theorem relates the flow of a vector field through a closed surface to the behavior of the field inside the surface. Stokes' theorem relates the flow of a vector field along a closed curve to the behavior of the field over the surface bounded by that curve. These are not simple extensions. They are deep and beautiful results, but they all begin with the same core insight: the relationship between a change at a point and the accumulation of change over a region. They are the culmination of the calculus of Newton and Leibniz, extended to the full complexity of the physical world. And there is also the study of sequences and series, which is a branch of calculus that deals with infinite lists of numbers. A sequence is an ordered list of numbers, like 1, 1/2, 1/3, 1/4, and so on. A series is the sum of the terms of a sequence. Some series converge to a finite value, and some diverge to infinity. The study of convergence and divergence is a central topic in calculus. One of the most famous series is the geometric series, which is the sum of a constant ratio raised to increasing powers. If the ratio is less than 1, the series converges to a finite value. If the ratio is greater than or equal to 1, the series diverges. Another important series is the Taylor series, which allows you to represent any smooth function as an infinite sum of power terms. This is a powerful tool for approximating functions. It allows you to calculate the value of a complicated function by adding up a series of simpler terms. For example, you can calculate the value of the exponential function, or the sine function, or the cosine function using their Taylor series. This is how calculators and computers actually compute these functions. They do not look up the value in a table. They add up the first few terms of the Taylor series, and they get an approximation that is accurate enough for any practical purpose. So sequences and series are not just abstract mathematical objects. They are the computational engine of modern mathematics. They are the bridge between the continuous and the discrete, between the world of calculus and the world of digital computers. So where does calculus live in the world tonight? It lives in the phone that might be on your nightstand. The phone uses calculus to process signals, to compress images, to control its battery, and to navigate using GPS. GPS in particular would be impossible without calculus. The system of satellites that orbits the Earth uses the principles of calculus to account for the effects of relativity, both special and general. The clocks on the satellites run at a different rate than clocks on the Earth's surface, and calculus is needed to correct for that difference. Without these corrections, GPS would be wrong by several kilometers. The phone also uses calculus to interpret your touch on the screen. The screen detects changes in capacitance, which is a measure of the ability of a material to store electrical charge. The processing of that signal involves filtering, smoothing, and differentiation. The phone uses calculus to predict what you are going to type next, using models that are trained using optimization algorithms, which are themselves based on calculus. The phone's camera uses calculus to focus the lens, to adjust the exposure, and to process the image. The algorithms that compress the image, making it smaller so that it can be stored or transmitted, are based on calculus. The algorithms that enhance the image, making it sharper and clearer, are also based on calculus. So your phone is a little machine that runs on calculus. Calculus lives in the building you are in. The architects and engineers who designed it used calculus to understand the stresses and strains on the beams, the flow of heat through the walls, and the distribution of weight in the foundation. They used calculus to predict how the building would sway in the wind and how it would settle over time. They used calculus to design the electrical systems, the plumbing systems, and the heating and cooling systems. Every time you turn on a light, you are benefiting from the calculus that was used to design the electrical grid. Every time you turn on a faucet, you are benefiting from the calculus that was used to design the water system. The flow of water through the pipes, the pressure at the faucet, the time it takes for the hot water to reach you, these are all governed by differential equations. Calculus lives in your body. Every time you take a breath, the air flows into your lungs in a way that can be described by calculus. The flow of air in your airways is governed by the principles of fluid dynamics, which are expressed as differential equations. Every time your heart beats, the blood flows through your arteries and veins in a way that can be modeled by calculus. The pressure, the flow rate, and the resistance to flow are all related by equations that involve derivatives and integrals. The concentration of medicine in your bloodstream, the spread of heat through your skin, the growth of your hair and nails, these are all processes of change and accumulation. They are all processes that can be understood through the lens of calculus. The neurons in your brain fire in patterns that are being studied using mathematical models that involve calculus. The very act of thinking, of processing information, can be modeled using calculus. And calculus lives in the sky above you. The motion of the clouds, the path of the moon, the orbit of the Earth around the sun, all of these are described by differential equations. The laws that govern them are laws of change. They are laws that Newton formulated using his calculus. And tonight, you are moving through space, tracing a path that is determined by those laws. You are living in the world of calculus, even as you lie perfectly still. The stillness you feel is a kind of illusion, a local illusion. In the grand scheme of things, you are in constant motion, and calculus is the language that describes that motion. There are also some harder questions, some strange things about calculus that mathematicians still think about. One of these is the nature of infinity. Calculus relies on the concept of an infinite process, the idea of taking a limit as a number approaches zero or infinity. This is a difficult concept to make entirely rigorous. There are paradoxes and puzzles that arise when you think about infinity too deeply. Zeno's paradoxes, ancient Greek puzzles, are essentially about the nature of infinity and change. Zeno argued that motion is impossible, because to move from one point to another, you must first cover half the distance, and then half the remaining distance, and so on. This would require an infinite number of steps, which he argued could not be completed. Calculus resolves this paradox by showing that an infinite number of steps can indeed sum to a finite total. The infinite sum of 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, is equal to 1. This is a convergent infinite series, but the paradox still raises questions about the nature of infinity. Is infinity a completed whole, or is it a process that never ends? This is a philosophical question that has been debated for millennia. Another strange thing is the existence of functions that are continuous everywhere, but differentiable nowhere. That is, functions that have no sharp corners, no discontinuities, no breaks, but that are so bumpy, so jagged at every scale, that you cannot define a tangent line at any point. These are called nowhere differentiable functions. They were first discovered by the mathematician Carl Weierstrass in the 19th century. He constructed a function that is continuous, meaning it has no jumps, but it has a corner, a cusp, at every single point. This was a shocking discovery at the time, because it showed that the intuitive idea of a continuous function as a smooth curve was wrong. There are continuous functions that are nothing like smooth curves. They are fractal-like objects, infinitely complex. These strange functions are used to model things like the stock market, the movement of small particles in a fluid, and the shapes of coastlines. And there is the question of the continuum. Is the number line truly continuous, or is it made up of discrete points? This is a foundational question in mathematics, and it is related to the foundations of calculus. There are different systems of mathematics, different axiom systems, that give different answers to this question. The standard system, Zermelo-Fraenkel set theory with the axiom of choice, assumes that the number line is continuous. But there are other systems, like non-standard analysis, that introduce infinitesimals as actual numbers. These are numbers that are infinitely small, smaller than any positive real number, but not zero. This is a different way of formalizing the ideas of Newton and Leibniz. And mathematicians are still exploring these systems, still trying to understand the deepest structure of the mathematical universe. These are not questions with easy answers. They are open questions, areas of ongoing research. But they are part of the beauty of calculus, the fact that it opens up new questions even as it answers old ones. It is a field that is alive, not dead, a field that is still growing and changing. By now you may have drifted in and out a few times. That is exactly right. There is nothing to catch up on. Everything has been settling quietly, whether you were following closely or not. If you were to hold all of tonight in one image, it would be this. Imagine a wide river flowing gently through a landscape. The river is always moving, always changing. The water at any one point is flowing at a certain speed, a certain direction. That is the derivative, the rate of change at a single point. Now imagine the total amount of water that has passed a given point over the course of a day. That is the integral, the accumulation over time. And the relationship between the flow at a point and the total flow over time, that is the fundamental theorem. They are two sides of the same river. You cannot have one without the other. The river is the world of change, the world of motion and growth and flow. And calculus is the way we understand that river. It is the map of the river, the language of the river. It is not the river itself, but it is a way of seeing the river clearly. And that is what calculus really is. It is not a set of rules. It is not a collection of formulas. It is a way of looking at the world, a way of noticing that everything is in motion, and that we can understand that motion by breaking it down into tiny pieces and then putting it back together. It is a way of thinking about change. And that way of thinking, once you have it, changes the way you see everything. You see the curve of a falling apple, the arc of a thrown ball, the growth of a tree, the decay of a radioactive atom, the flow of traffic on a highway. All of these are part of the same story. They are all examples of things changing, of quantities flowing, of processes accumulating, and they can all be understood with the same basic tools: the derivative and the integral, the taking apart and the putting together. That is the full picture of calculus. Now, let us return to the derivative one more time to see it in a slightly different light. The derivative is often described as the slope of a tangent line. But what does that really mean? A tangent line is a line that just touches a curve at a single point. It is the line that best approximates the curve at that point. If you zoom in on the curve at that point, the curve becomes more and more like the tangent line. In the limit, as you zoom in infinitely, the curve and the tangent line become indistinguishable. So the derivative is the slope of the line that the curve becomes when you zoom in infinitely. This is a powerful way of thinking about the derivative. It is a way of making a complex shape simpler by focusing on a tiny piece of it. And this idea of zooming in, of looking at a system on smaller and smaller scales, is one of the most important ideas in all of science. It is the idea that underlies the microscope, the telescope, and the study of atoms and subatomic particles. And it is the idea that underlies the derivative. It is the idea that a complex whole can be understood by understanding its smallest parts. And let us return to the integral one more time as well. The integral is often described as the area under a curve. But what does that really mean? Imagine you have a curve on a graph. The area under that curve is the sum of the areas of infinitely many, infinitely thin rectangles. Each rectangle has a height equal to the value of the function at that point and a width that is infinitely small. The integral is the limit of the sum of these rectangles as their width approaches zero. This is a very concrete way of thinking about the integral. It is a way of calculating the total of a quantity that varies continuously. And this idea of summing up tiny pieces is also one of the most important ideas in all of science. It is the idea that underlies the concept of work, of energy, of mass, and of many other physical quantities. It is the idea that a continuous whole can be understood as the sum of its tiny parts. Now, there is one more thing about calculus that is worth mentioning, and that is its relationship to the physical world. Calculus is not just a mathematical abstraction. It is a tool for understanding the universe. The laws of physics are written in the language of calculus. Newton's second law of motion, which states that force equals mass times acceleration, is a differential equation. Acceleration is the derivative of velocity, and velocity is the derivative of position. So Newton's second law is an equation that relates a force to the second derivative of position. This is the fundamental equation of classical mechanics. It is the equation that describes the motion of everything from a falling apple to an orbiting planet. Maxwell's equations, which describe the behavior of electricity and magnetism, are a system of partial differential equations. They describe how electric and magnetic fields change in space and time. They are the foundation of all of electrical engineering, and they led to the discovery of radio waves, X-rays, and light itself. And Einstein's theory of general relativity, which describes the force of gravity, is also a system of differential equations. It describes how the presence of mass and energy curves the fabric of space and time. So calculus is the language of the universe. It is the language in which the laws of nature are written. And by learning calculus, you are learning to read that language. It is like learning to read the music of the spheres. And calculus is also the language of economics, of finance, of biology, of medicine, of computer science. In economics, calculus is used to model supply and demand, to optimize production, and to forecast economic growth. In finance, calculus is used to price options, to manage risk, and to model the behavior of markets. In biology, calculus is used to model population growth, the spread of disease, and the dynamics of ecosystems. In medicine, calculus is used to model the flow of blood, the diffusion of drugs, and the growth of tumors. In computer science, calculus is used to design algorithms, to optimize machine learning models, and to analyze the performance of computer networks. Calculus is everywhere. It is the language of change, and change is everywhere. It is the common thread that connects all of these different fields. Now, let us think about the idea of the derivative in terms of everyday experience. When you drive a car, you are constantly making decisions based on derivatives. The speedometer gives you the derivative of position with respect to time. The accelerator pedal controls the derivative of speed, which is acceleration. The steering wheel controls the derivative of direction, which is curvature. So you are using calculus intuitively every time you drive. When you cook a meal, you are making decisions based on rates of change. You are watching the temperature of the pan, the color of the food, the rate at which the water is boiling. You are making judgments about how fast things are changing, and you are adjusting your actions accordingly. When you exercise, you are aware of your heart rate, your breathing rate, the rate at which you are sweating. You are monitoring the rates of change of your body's systems. Calculus is not an abstract thing. It is a fundamental part of how we perceive and interact with the world. It is a part of our everyday intuition, made precise and powerful. And let us think about the integral in terms of everyday experience. When you save money, you are accumulating a total over time. The total is the integral of your savings rate. When you fill a bathtub, the amount of water in the tub is the integral of the flow rate from the faucet. When you walk, the distance you have traveled is the integral of your speed. So the integral is also a fundamental part of how we experience the world. We are constantly accumulating things, steps, breaths, experiences, memories. And the integral is the mathematical way of capturing that accumulation. It is the way we measure the totality of a process. There is a deep connection between calculus and the concept of infinity. The derivative involves a limit as a time interval approaches zero. The integral involves a limit as the number of rectangles approaches infinity. So calculus is, in a very real sense, the mathematics of infinity. It is the tool that allows us to handle the infinite in a finite way. It allows us to make precise statements about things that are infinitely small or infinitely large. This is a profound and powerful idea. It is the idea that allowed Newton to understand the motion of the planets. It is the idea that allowed Leibniz to develop a powerful new notation, and it is the idea that underlies much of modern science and technology. The infinite is not something to be feared, it is something to be understood. And calculus is the tool for that understanding. It is the bridge between the finite and the infinite. And so, as you drift through the night, you might think about the fact that you are a living example of the ideas we have been discussing. You are a function of time. Your position in space is a function of time. Your temperature is a function of time. Your thoughts are a function of time. Everything about you is changing, constantly, from moment to moment. And calculus is the language that describes that change. It is the language of your existence. And that is a beautiful thing to think about as you lie here in the quiet of the night. You are not a static object. You are a process. You are a flow. You are a river moving through time. And calculus is the map of that river. There is a kind of peace in this understanding. It is a peace that comes from knowing that change is not chaos. Change has structure. Change has rules. Change can be understood. And that understanding brings a sense of calm. It is a sense of calm that comes from knowing that the universe is not random, but ordered. It is a sense of calm that comes from knowing that we have a way of seeing that order, and that way is calculus. It is not a way that is difficult or intimidating. It is a way that is natural and intuitive. It is a way of paying attention to the world around us. It is a way of noticing the flow, the change, the motion, and it is a way of finding beauty in that motion. The derivative, the integral, the fundamental theorem, these are not just mathematical concepts. They are ways of seeing. The derivative is a way of seeing the present moment, of seeing how things are changing right now. The integral is a way of seeing the whole journey, of seeing how the present moment is connected to the past and the future. And the fundamental theorem is a way of seeing the unity of these two perspectives, a way of seeing that the present moment and the whole journey are connected. They are two sides of the same coin, and that is the message of calculus. That is the lesson of the river. Everything is connected, everything is flowing, and everything is part of a larger whole. Part 4 of the fully expanded script continues here with the final closer. So tonight, as you let your thoughts drift, think about the river, think about the flow of the water, the movement of the current. Think about the way the river is always changing, never still. And yet, the river is also always the same river. There is a continuity to it, a consistency. The river flows from its source to its mouth, and it has been doing so for a very long time. In the same way, you are always changing, always flowing, always moving through time. Your cells are dividing, your heart is beating, your mind is drifting, and yet you are also always yourself. There is a continuity to you, a consistency. You are the same person who lay down to sleep tonight. And tomorrow you will wake up and you will be changed, but you will still be you. That is the quiet beauty of calculus. It is a way of understanding that continuity in the midst of change. It is a way of seeing the stillness in the motion. It is a way of knowing that even as everything flows, there are patterns, structures, and relationships that endure. And that knowledge is a kind of comfort. It is a way of making peace with the passage of time. The derivative tells you that things change, and the integral tells you that those changes matter, that they add up to something. And the fundamental theorem tells you that the two are connected, that you cannot have one without the other. So as you lie here, feeling your breath move in and out, feeling the gentle rhythm of your heart, know that you are a living example of these ideas. You are a function of time, you are a flowing quantity, and you are in the process of becoming. So let the motion of the world quiet itself. Let the river of thought slow to a gentle trickle. Let the night carry you where it will. You have understood more tonight than you may realize. And that understanding will be there in the morning, just as the river is still there, flowing as always. The ideas of calculus are not something you need to hold on to tightly. They are something that can rest gently in the background of your mind. They are like the steady hum of a distant engine, a quiet presence that you can feel even when you are not paying attention. And that is the gift of calculus. It is not a tool that you must master. It is a way of seeing that you can carry with you, even in your sleep. Think about the curve of a falling leaf, the way it drifts and turns on its way to the ground. That curve is a function of time, a path that changes with every gust of wind. The leaf's speed, its direction, its acceleration, these are all derivatives. And the total distance it travels, the total path it takes, that is an integral. The leaf does not know calculus, but the leaf is living calculus. And so are you. Every breath you take is a flow rate. Every heartbeat is a pulse. Every thought is a change in the electrical activity of your brain. You are not separate from the mathematics of change. You are an expression of it. And that is what makes calculus so gentle. It is not a foreign language imposed on the world. It is a language that the world already speaks. It is the language of the wind, the water, the stars. It is the language of your own body. And by learning to hear that language, even just a little, you become more attuned to the quiet rhythms of existence. You become more aware of the flow, the motion, the change. And that awareness is not a burden. It is a release. It is a letting go of the need to hold things still, to freeze them in place. It is an acceptance of the fact that everything is moving, everything is changing, and that is exactly how it should be. So tonight, as you drift towards sleep, let the ideas of calculus settle into you like a gentle rain. Let the derivative remind you that change is natural, that the present moment is always in motion. Let the integral remind you that those changes add up, that every small moment matters, that you are accumulating a life, a story, a journey. And let the fundamental theorem remind you that these two things are one, that the instant and the whole are connected, that you cannot have the present without the past, or the future without the present. You are a river, flowing from your source to your mouth. You are a function, mapping time to experience, and you are beautiful in all of your motion and change. Now, as the night deepens around you, let go of any need to hold on to these thoughts. They will stay with you, even if you do not try to keep them. They will settle into the quiet places of your mind, where they can rest and grow. There is nothing more you need to do tonight. There is nothing more you need to understand. You have already done the work, simply by listening, and that listening is enough. The room around you is still. The air is calm. The world outside is quiet. And inside you, the flow continues, steady and gentle. Your breath moves in and out, a rhythm that has been with you since the moment you were born. Your heart beats, a pulse that has never stopped. Your mind drifts, a river of thought that flows on its own. You are in the hands of something larger than yourself, something that has been flowing for billions of years. And you are a part of it. You are not separate. You are not alone. You are part of the great river of existence, flowing and changing, always becoming. So let the river carry you. Let the current take you where it will. There is no need to steer. There is no need to steer. There is no need to steer. There is no need to gentle flow, the quiet motion, the peaceful drift. And in that drift, you will find rest. In that flow, you will find sleep. And in that sleep, you will find the deep, quiet peace that comes from knowing that all is well, that all is flowing, that all is exactly as it should be. So rest now. Sleep well. Good night.